Kyle, stop talking, I'll throw you out. 29. How many moles of aluminum are needed to react completely with 1.2 moles of FeO? What's nice is, and you're welcome, it's already balanced. 2 ALs, the S just simply means solid, you don't really need that. 3 FeO, how do you pronounce that? What's that, FeO? Iron oxide, but in particular, it's really iron what oxide? What Roman numeral? How do you know it's a 2? Could have been a 3. How do you know it's a 2? Nice. Yeah, because oxygen has 2, and it's 1-to-1 ratio. That's correct. Very good. Okay, so I think I did it right. And we start with 1.2 moles of FeO, so we're right here. And it's moles. I've been teaching you grams to moles to moles to grams. But if they're already starting you in moles, you don't have to deal with the gram part. Fine. And they want to know how many moles of aluminum. Fine. You don't need that one either. So it's a pretty quick deal. So it's 1.2 moles of FeO over 1. And we're going to moles of the next substance, which is, we're going mole to mole. The new substance we want to go to is aluminum. And aluminum has 2 moles. There's a 2 in front of it. And this label has to go down below over here. So we're going to have moles of FeO. Well, how many moles? 3. When you do this math out, you get the correct answer of 0.08. The answer is B. 130. The equation below shows the decomposition of lead nitrate. If you didn't remember what decomposition was, I'm telling you, or this question is, it's telling you that's what decomposition looks like. Use that to go answer other questions if you need it. But anyway, decomposition of lead nitrate. How many grams of oxygen are produced when 115 grams of NO2 are formed? Wow, I don't feel like writing this whole thing out. That's a 2. This looks horrible. NO3, 2, breaks down into lead 2 oxide plus 2 plus O2. It's already balanced. That's nice. We're going to start with 11.5 grams of NO2. That's what's produced. And they want to know how much oxygen was needed. So we're going from here. Nope. That's not what I'm looking for. We want to know how many grams of O2 are produced. So we're going from here and there. And let's see. So it's 115 over 1. I mean 11.5 over 1. Then it's going to be 46 grams of NO2. I round off heavily. 1 mole of NO2. Times, now you're going to go moles to moles. You need moles of NO2 down below. And I know that moles of NO2, there are 4. To moles of O2. And there's a 1 mole of O2. And then I need moles of O2 down here. And it weighs 32 grams. Do the whole thing out. Get the math done, and you're going to end up with an answer of 2 grams. The answer is B. You multiply all the top, then divide by everything on the bottom. Divide by 46 and divide by 4. 131. How many moles of H3PO4 are produced when 71 grams reacts completely with H3PO4? I'm not doing the whole thing out. The answer is B. 1 mole. It follows the same understanding as before. The next one I write out would be a limiting one. I'll show you how to do one limiting one. I don't want to keep doing all these. You do have several of these, and they will take time. So that's why I said skip them. Go do other things first. 132. When two substances react to form products, the reactant which is used up is called the limiting reagent, B. It limits because you had more of the other stuff, but you can't go any further because this one's used up. 133. How many grams of chromium are needed to react with an excess of CuSO4 to produce 27 grams of copper? Correct answer is 14.7. A. Once again, it's just like the others. When an equation is used, this is 134. When an equation is used to calculate the amount of product that will form during a reaction, the value obtained is called what? We're using an equation. It's not like we're doing it actually in lab. So when you do the equation 1 and you calculate, that is your theoretical. When you actually perform it in lab, that's your actual. And we said if you want percent yield, it would be actual over theoretical times 100. You'll get your percent yield. And usually the higher the percent yield, the more careful you've done the experiment. Some experiments, though, you can't help it, they just don't get a good yield. They don't react that well, given the conditions that you have. So you get a low percent yield. If you get a percent yield of 3%, that's probably not good. 135. The element chromium has 4 naturally occurring isotopes. This one's important. Let's see. Use the relative abundance of each to calculate the average atomic mass. So I have chromium 50, that's its mass, 50, and that is found 4.34% of the time. Then I have chromium 52, and that is found 83.79% of the time. Then I have chromium 53, and chromium 54. 53 is found 9.5% of the time. 54 is 2.37% of the time. I want to know what number would I actually get for chromium on the periodic table if that were the case. Because the numbers on the periodic table aren't nice and clean and no decimals. They have decimals. The reason they have decimals is because of their percent abundance in nature. So they have different abundances for different masses or isotopes of chromium. The way you do it, it's as easy as this. 50 times 4.34% plus 52 times 83.79% plus 53 times 9.5% plus 54 times its percent. When you do that out, you get numbers like, when you do this one, it's 2.17 plus 43.6 plus 5.0 plus 1.28. You add them all up, you're going to get an answer of 52.05. Okay, that's how you get them. Yeah, or you do this, 50 times, you could say 0.0434, putting it in decimal form, or on your calculator, you could do 50 times 4.34%. When you hit the percent key, it's going to shift it over anyway. Either way, whichever one you want, but it's a matter of you take each one and you add it, and you should get a number that's close to what these numbers were, and you should get a number probably that's closest to the one that is the highest percent. In this case, 83%. More than likely, my number should be around this one, and it is. Because that's the one that's the most predominant. That's a big word. All right, 136. Going red now. The electron configuration for a neutral atom of beryllium. That's important that you see the word atom versus ion. Because when it's an atom, what that means is I have the same number of protons as neutrons, and I know protons based on the atomic number. When I say ion, the number of protons does not equal the number of electrons. It's either greater or less, depends if it's positive or negative. So therefore, they're telling me it is a neutral. You don't have to use the word neutral, but they're telling me it's beryllium. And when you do the periodic table deal and all that, beryllium is right about here, if I did it right. And this is going to be a 1s2, 2s2, and you're done. That's it. Beryllium is atomic number 4. It's an atom, so it's got 4 electrons, and here they are. 2, 4. Done. 137. We're looking for chlorine atom. Chlorine, once again, you can find out where it's located. You can find out where it's located. It's over here. And you could do the thing of 1s2, 2s2, 2p6, 3s2. Oops, it's bad. Whatever. 3s2 and then 3p5. and that is chlorine with no charge. If it was chlorine ion, then it's whatever chlorine does to become like a noble gas. And in this case, chlorine gains one electron if I said ion, and you would just have it as a 3p6. One more. Next one. 138. I will give you this formula. Do you remember this one? Speed of light is equal to wavelength times frequency. It's been a while since we've seen that. Given to you on this problem is the speed of light, which is 3.00 times 10 to the 8th meters per second. And a wavelength is given to us, and that's what this is, lambda. Wavelength is 2.94 times 10 to the negative 8 meters. Very nice of me to choose one that's in meters and meters. Versus, remember converting nanometers to meters? We did, but anyway. So, they want to know what is the frequency, and that's what that stands for, frequency. You rearrange the formula. Frequency is equal to speed of light over wavelength. Frequency is equal to 3.00 times 10 to the 8th meters per second over the wavelength, which is 2.94 times 10 to the negative 8, and that's in meters. And what's going to happen is meters cancel. I'm going to have frequency in per seconds. What's another term for per second? Hertz, thank you. Or you could put hertz. And let's see. Final answer for that is 1 times 10 to the 16th. If you do the calculations wrong, you might have 1 times 10 to the, I don't know what you would get actually. But you are, remember you have to use the EE key. Some of you mess up and it doesn't work properly. Or at least use parentheses down here. I don't want to explain that whole thing again. Anyway, that's your answer. 139. 139. Which group of elements in the periodic table is known as the alkali metals? For groups, you should know a few groups. Whatever. That's really, keep messing this up. Anyway, this first group are alkali metals. Therefore, that's your answer. It's group 1. The second group is alkaline earth metals. Then we're going to go to group 7A, 7 valence electrons. Those are called your halogens, like a halogen light made with those gases. Bromine is a common one. And then you have at the end your noble gases. And then lastly, we'll care about these. These are called what? I had this earlier. Transitional metals. You should know these. And we'll be okay with the others. You don't have to memorize those down below. Okay, the next one. Number 140. An element has an atomic number of 80. So I have some element and it's got an atomic number of 80. Atomic number goes down there. How many protons? Well, I know right off the bat it's got 80 protons because that's the same as atomic number. How many protons, how many electrons are in the atom of this element? They're saying the word atom, told you earlier. Protons then will equal electrons, so therefore I've got 80 electrons. And that's your answer, 80 and 80. Give the electron configuration for boron and its ion. So it's really a two-part question for 141. Well, boron is going to be 1s2, 2s2, 3p1, correct? Its ion, boron is going to do what? Is it going to add electrons or lose electrons if it's in group 3? Lose. So it's going to end up losing 3 and it's going to end up looking like helium. It's going to have a configuration of helium when it's lost 3 electrons, 1s2. That's it. And let's see, two more to go. 142. Write the formula for barium oxide. Barium plus oxygen, cross them over, you get a 2 and a 2, and you got to switch. You got to reduce it. So BaO. 143. Boron chloride is BCl3. What you don't have in here is something like this, and that ends that section. But what I haven't shown you is empirical formula. You got empirical formula, and you have molecular formula. We haven't done that, and we haven't done percent composition. But those videos are on the website just below where I post these. Okay? Thank you. All right, so let's see. So my mistake is this right here. That should be a 2P1. Thank you, Tegan.